Good day, dear friends. My name is Evgeny Proskrin. I'm the founder of ATF Group. This is an engineering and manufacturing group of companies that started in a garage, producing hardware for transformers. And now it offers digital solutions for a wide range of industrial sectors. Today we are launching a series of micro lessons to share practical knowledge and help our energy sector operate more reliably, efficiently, and safely. After all, our mission is simple: your energy under our protection. In the previous video, we explored the three types of transformer losses: no load, load, and stray. We discussed how each type forms and how it affects the economics of transformer operation. Today, we'll focus on the core, the main source of no-load losses, and examine how material selection, processing methods, and geometry influence transformer efficiency and lifespan. The magnetic core forms a closed path for magnetic flux and is the main contributor to no-load losses. These losses consist of two components: hysteresis losses, which depend on the area of the hysteresis loop in the steel; eddy current losses, which depend on sheet thickness and electrical resistivity. The design goal is to achieve high magnetic permeability with minimal losses. The formula for hysteresis loss includes frequency, magnetic induction, and a material-dependent coefficient. Today's cores use cold-rolled, grain-oriented electrical steel. Over the past 30 years, no-load losses have been reduced by a factor of 2 to 2.5. For example, in the 1980s, typical steel losses were about 1.4 watts per kilogram at 1.7 Tesla. Modern grades now achieve 0.9 to 1.0 watts per kilogram under the same conditions. In one case, switching to improved steel reduced core losses by 1.2 kilowatts in a 160 megavolt ampere transformer. At an induction level of 1.5 Tesla, the loss density for high-quality steel is below 1.05 watts per kilogram. Grain orientation in the steel matters. When grains are aligned with the magnetic flux, hysteresis losses drop by up to 30%. Orientation techniques include controlled rolling, laser surface treatment, thermal processing. The higher the grain alignment, the smaller the hysteresis loop, and the lower the loss. Core processing technology also plays a crucial role. Laminated construction, stacking thin sheets, reduces eddy currents. Sheet thickness typically ranges from 0.23 to 0.30 millimeters. Thinner laminations can reduce eddy losses by up to 25% compared to solid cores. Sheets are coated with insulating varnish or oxide layers to prevent current flow between them. In one case, switching from 0.3 to 0.23 millimeter sheets reduced losses from 3.5 to 2.8 kilowatts in a 100 megavolt ampere transformer. Losses are influenced by voltage, frequency, and magnetic induction. Eddy current losses increase with the square of both frequency and magnetic flux. Higher voltage or frequency requires thinner, more heat-resistant steel. For example, raising the frequency from 50 to 60 hertz increased losses by 12 to 15%. Core geometry is another important factor. Losses depend on yoke shape, cross-sectional area, and assembly quality. Reducing air gaps and misalignments lowers magnetic resistance and associated losses. In one study, reshaping the yoke in a three-phase transformer reduced losses 0.6 kilowatts without changing the steel type. There are also modern alternatives to traditional steel. Amorphous alloys, based on iron, silicon, and boron, can cut losses to 0.3 to 0.5 watts per kilogram. However, they are mechanically harder to process and mostly used in distribution transformers. Nanocrystalline alloys reduce losses by up to 70% but are significantly more expensive. They are promising for compact or high-frequency transformers. Conclusion: these materials are cost-effective when electricity rates are high or space is limited. Practical task: you're working with a 160 megavolt ampere transformer. No load losses equals 5.5 kilowatts. Core steel thickness equals 0.30 millimeters. Specific loss equals 1.1 watts per kilogram. You switch to 0.23 millimeter steel with a specific loss of 0.9 watts per kilogram. Your tasks: calculate the percentage and kilowatt reduction in losses. Estimate long-term savings over 25 years based on standard energy rates. If the material upgrade adds $150,000 to the project cost, is the improvement economically justified? At what energy cost would the switch no longer be viable? Today you've learned how steel properties affect no-load losses in a transformer, why sheet thickness, grain orientation, and lamination are key design parameters, when it makes sense to use advanced materials, and when it doesn't. In the next video, we'll learn how to calculate loss capitalization, how engineers compare designs and make economically justified decisions. Want to explore the topic in more depth? Visit our website. The link is in the description. Interested in real-world solutions and industry challenges on this topic? Contact us. Our details are on the screen. Want to become a part of the global energy flow? Reach out to us. You'll find our contacts on the screen.